Hello, my name is Georgi Radulov from Eindhoven University of Technology, and I would like to welcome you to my presentation about a 0.037 square millimeters, 1 gigasample per second, 12-bit self-calibrated 40 nanometer CMOS DAC cell with SFDR more than 60 dB up to 200 MHz and IMD3 less than minus 60 dBc up to 350 MHz. This is work done together with Patrick Quinn. So it's all about small data converters which will enable massive arrays. And the motivation for this is that now today we have a lot of processing power in digital domain, but the world that we live in is still analog. And unavoidably we need the conversion from digital to analog in order to benefit from the advantages of digital domain. And we want to do more. And more comes with redundancy. And luckily the progress favors redundancy. For example, spatial selectivity in telecommunication. And spatial selectivity is something very much needed, for example, in 5G standards where phased arrays are needed. So 5G actually channels the information that is transmitted in a certain direction. And this is done by multiple antennas in a phased array. And if we want to control from digital domain in a very accurate way this beam, and if we want to have even more beams, so we have if we want to have multi-beam communication, we need to go to digital beamforming. And to go to digital beamforming means that from digital to antenna, this should be replicated in separate channels, which means that you have to use digital to analog conversion per antenna. And we are talking about 16 256 D2A converters in parallel. The problem is that if they are not integrated, so basically you use say a single chip per D2A converter, and then the integration is on PCB level, there will be some interconnection between the digital processor and the DAC. And this will be very, very expensive in both in terms of power, but also the quality of the signal in terms of synchronization. These buses will be enormous. At high speed, you have to use differential LVDS signaling, and you have to propagate the signal up to a certain distance. And if you use PCB and if you use DAC chips in a PCB, large arrays of them, they occupy the area, so you have to propagate these signals to larger area. This will create a lot of problems with synchronization, but also will require a lot of power to drive at high speed these signals. So what you want is to put these D2A converters inside the digital processor. In order to be able to do this, you need first that each unit of these D2A converter cells is very small, extremely small, because the total area that they will occupy will multiply by the array factor. Another thing that you need is that each cell is very power efficient, because a single chip needs to handle all the power of the array. And in the same time, you want them to be high performance, still to meet the requirements, the tough requirements for wireless telecommunication. And this is a problem. So the problem with in this trade-off, the problem of combining high performance and small area is as follows. So high performance, first let's define high performance. What we understand by high performance is wide band, which means high sample rate, and high linearity. Wideband directly prohibits oversampling, so you cannot use digital sigma delta. And this leaves us with the standard architecture for D2A converters, which is a flash architecture. And now the other requirement about high linearity. High linearity actually requires small errors. So if we think in D2A converters about small errors, we think immediately about unary architectures. The problem there is of course the area. So if we want to minimize the area, we think about binary D2A converters. But binary D2A converters feature a lot of errors, and especially the mid-transition errors, which generate a lot of harmonic distortion. And this applies to amplitude errors and timing errors for binary architectures. So this means that if we want to enable massive integration of D2A cells, and we want them to be small, power efficient, and fast, we have to enable binary D2A converters with small errors. And the way to do this is through calibration. Calibrating the errors of binary D2A converter is key to small area high performance and hence to massive arrays. And this is the main hypothesis of this work and the main topic of this presentation. So this brings me to the contents of my presentation today. I'll continue with binary and unary current steering digital to analog converters and explore the trade-off. Then I'll introduce the calibration for binary converters, present our proof of concept, a small area 12-bit DA converter cell in 40 nanometer CMOS, its massive integration into an array of 16. I'll show some measurement results, and at the end I'll draw conclusions. First of all, how do we make a current steering DAC? So this is the main abstract equation for digital to analog converter. So we have here the analog output A, which is actually the product of the digital word and two references, an amplitude reference and a timing reference. The digital word is just a series of ones and zeros, digital data. And in order to convert this digital data to the analog word, we need to align it to a certain rate. This is the timing reference, the clock, and certain amplitude. This is, for example, the full scale range of the DAC. We can expand this product into multiple terms. So each term will contain a single bit of information and a weighted reference. And the timing reference will be applied via the switches. So this here will be the decoder, the synchronization, clock distribution drivers. This multiplication will be the switches, and the sum of all these terms is actually the summation network. This approach is the main approach used today to implement, to realize physically the digital to analog converters, current steering digital to analog converter. And here is the generic floor plan that is widely used. So you have digital domain here and the analog domain there. They don't mix, they don't overlap. We keep them separate. Then you create actually these 1-bit cells, and these 1-bit parallel slices. They are these terms. So all their contributions is collected here in the summation network, and here is where the analog signal is extracted. So a slice contains at least a synchronization latch, a driver for the DA switches, and a DAC output cell, which is output cascades, DA switches, and current source cascades. The pitch between these parallel slices is usually kept the same, and this has to do with modularity in the layout. Now the choice of the number of slices determines actually the segmentation that we will use, and this is a major choice for the area, the resources, the efficiency, and the performance of the DA converter. Now, the two extremes for the choice of segmentation is either binary, very efficient, or unary, very good performance. Here I illustrate the binary architecture. We have the codes here, and we create the analog output value by a proper combination, depending on the codes, of 4 references, of 4 components. Of course, as the resolution grows, so this staircase grows, we will use more components. But here the point is that in binary architecture is very efficient. We use only a few switches, only a few cells, and then the analog outputs are created by combinations of these. The problem with binary architecture is when the mismatch comes, when these references are not exactly as designed due to the tolerances of the manufacturing technology. Then this nice stairway becomes very distorted, particularly at mid-scale. At mid-scale we will have large errors, and this is, for example, here illustrated with the mid-scale non-monotonicity, for which, even though we increase here the code by 1, the analog output actually decreases. This deteriorates the performance very much. And the other extreme is the unary DAC architecture. In this architecture we use the same references for all cells that are being switched, which results in the problem that many resources are used. So you have many switches, many synchronization latches, many drivers. However, the performance is very robust. Even if you have mismatches, they only remain local mismatches. So generally, the performance is much more linear. So you don't have this third-order distortion pattern here, this very acute third-order distortion pattern. So now the question for us is, how can we utilize the efficiency of binary architecture while minimizing their errors? And our answer is calibration. But calibration of binary currents is not trivial. Calibration of unary currents is easier because you have the unary currents and then they're all the same, and then you calibrate them against common reference, and that's it. The challenge in binary converters is that you need to calibrate each binary reference to an exact portion of the reference, to 1/2, 1/4, 1/8, etc., etc., etc. And this is the challenge: how you calibrate the binary currents to an exact portion of the reference. And here is our algorithm, how we do it. So for our algorithm, what you need is 2 sets of binary currents, or 2 digital to analog converters, binary digital to analog converters. And then the algorithm is as follows. So here I illustrate this with a scale, but in practice this is done for calibration of current, so we use current comparator. So on one side we have a reference, and on the other side we put the MSB current of the first set, and all the other currents, plus 1 LSB. In other words, what we have here is all the currents of the first binary DAC cell, and then this is nominally, of course, equal to the reference. However, because of mismatch, the scale, the current comparator will show this branch is higher or smaller. If it's smaller, what you know, if it's lighter, you need to add some current to balance the scale, to balance the current comparator, or subtract current if needed. And this is what you do, and adding, subtracting current from the MSB of the first set, the MSB current of the first set. So you add a little bit current or subtract a little bit current from it through a calibrating DAC until the scale changes its sign. So this is an indication that both inputs of the current comparators are approximately equal to within the quantization error of the calibrating step. If you reach this point, you remove the MSB current from the current comparator and you put in its place the MSB current of the other set, of the other binary DAC. So this is the MSB current of the other set. So this is the same here. O is the same. Of course, now the scale will change. The current comparator will indicate one side to be bigger, and then you compensate again by adding or subtracting a little bit current through a calibrating DAC from the MSB current of the second set until both terms are equal, until the current comparator changes its sign. When you reach this point, what you know is that the MSB current of the first set is exactly equal to the MSB current of the second set within the quantization error of the calibration, within one quantization step of the calibration. And this is because this and this and this and this are the same, so they don't change. In step 3, what you want to do is to not only the MSB of the first set and the MSB of the second set to be equal, but you want their sum to be equal to the reference. So if they are equal between each other and their sum is equal to the reference, this can only mean that each of them is 1/2 of the reference. And this is how you calibrate to an exact portion, in this case 1/2 of the reference. So you connect the MSB of the first set and the MSB of the second set on one side of the current comparator, and on the other side is of course the reference, and then you change the calibration DAC, so you add or subtract current simultaneously of DAC 1 of the MSB of set 1 or set 2. If you change it simultaneously, you still keep both currents the same, but you change only their sum. And when their sum becomes equal to the reference, then each of them is equal to exactly half of the reference. So how to calibrate the next bit, MSB -1, it's illustrated here. The initial steps are the same as before, so on one side of the scale we connect all the currents of the first set, and then on the other side the reference, and we will change only the MSB -1 until the scale changes its sign, until the current comparator changes its sign. When this happens, we will remove MSB -1 of the first set, and at its place we will connect MSB -1 of the second set, of the second DAC cell. We will perform the calibration until this whole thing is equal to this whole thing, after which we know that this is equal to this, so the MSB -1 from the first set is equal to the MSB -1 from the second set, because this and this are the same. Then in the last step, what we do is that we connect on one side both currents, MSB -1 first set and second set. Normally they should equal to half of the reference, and then here we connect the MSB current of the first set, and here is the reference. Keep in mind that this current, the MSB current, is already calibrated to half the reference. So then, if we start changing MSB minus 1, both currents, in the same way, so that we keep both of them equal to each other, but then we change the sum, when this changes, when the current comparator output changes, this is an indication that the sum of these two currents is equal to the reference minus the MSB current. And the MSB current is already calibrated to half the reference, which means that each of the MSB minus 1 currents will be exactly equal to 1/4 of the reference, etc., etc. You implement this for all binary currents. So this calibration is a startup calibration, and it's only applied to amplitude errors. So to prove this in practice, we designed a 12-bit segmented 12-bit current steering DAC cell. So for this work we needed 12 bits, high sampling rate of 1 gigasample per second, and the application requirement is that we have to use thick oxide transistors. And thick oxide transistors are large transistors. So in this technology they were 280 nanometer. So this does not help with the area, but we had to do. Because we needed high performance, and we cannot calibrate timing errors for binary DACs. We chose some segmentation, so we allowed 4 MSB to be unary and 8 LSB, which is still a large portion, was binary. We calibrate everything, so all the unary and all binary with our algorithm. The reference, of course, is nominally equal to the unary current, so all the unary currents are calibrated to the reference, and then binary currents follow with the algorithm that I just presented. It had to be also high performance, so we could not use fully binary architectures. Still, we cannot calibrate timing errors. We can calibrate only amplitude errors. So this was the reason why we chose segmentation, which is 4 MSB bits unary and very large portion of binary LSB, 8 LSB binary. And to minimize all the dynamic errors, so that we keep good performance, good linearity at high frequency, most of the switching, digital part, is implemented in a low voltage CMOS logic with thin oxide transistors and also very small area, including the synchronization. And following the requirements of our applications, the output cell DAC stage needs to be in thick oxide transistors. So high voltage CML level shifters need to be used, and of course thick oxide drivers. So this is the architecture, this is the output stage of the DAC that we implemented. This is the main cell here, the DA switching output cell. This is the current source, and then in its drain a calibrating DAC is connected. So this calibrating DAC can generate correction current, either add or subtract correction current, so that I unary is actually adjustable. This is a current cascade, and at this point the current either goes to the DA switches for a normal DA conversion, or we can activate this, so we switch off this branch here, and the current is redirected through this probe transistor into the current comparator. And as you can see, that the current comparator here subtracts a reference current, and then the difference between this current and the reference goes to a current sign detector, which can detect 1 bit information, can give us 1 bit information, either current flows in or flows out, the difference current. And then this is read by the algorithm, and then the calibration DAC word is updated according to the algorithm that I just discussed in the previous slide. And this is the output cascade. So you see that all these transistors are actually thick oxide transistors. This is the requirement for the integration of the DAC unit inside the I/O bank. Other things which are interesting for this architecture, so the main novelty here is that we have one stage, one phase in the calibration algorithm for which we first calibrate for the gain mismatch of the DAC cell. In this way, we relax the requirements for the full scale range of the calibrating DACs per current source. So we have multiple parallel D2A converters, and the first thing that we do is that we will calibrate the gain error. And as the gain errors, so if they are mismatched, we will calibrate first the gain errors, and as the gain errors are minimized, or the full scale ranges of all DACs are the same, then we will calibrate the mismatch errors, so that we can utilize in a more efficient way the full scale range of the calibrating DACs which are embedded inside the DA cell. So this is one cell, and we have many of these in parallel, and in the output we sum up the current contributions. Another interesting thing about our architecture is using local cascade for biasing. This is the local cascade, so every cascade here is individually biased. So we generate at one place in the chip the biasing currents, and then locally, only locally, we translate this into a bias voltage for the current cascades. And we do this to isolate the different cells that we have here from seeing each other. So if you have a switching in one cell, it will not propagate this switching to the other cells through the biasing network of the cascades. Because why? Because the cascades are locally biased. Then we have these bleeding currents. Here are the bleeding currents, and the main purpose of the bleeding currents is to linearize the output cascades, so that these output cascades remain in saturation for different values here for different digital information switching M3 and M3 plus and M3 minus. These bleeding currents will always keep M4 plus and minus turned on and in saturation. Then the total output current is 20 milliamperes, which is terminated on a 50 ohm differential load. So this is the output cell. Then we have the digital train, starting from a digital bit, which is in digital domain, single-ended. Our first task is to translate this into a differential signal, and we do this in inside the master-slave latch, synchronization latch, and we split it here, and then we align with the clock. All this is in tin oxide, so that the timing is very accurate. And after that, this information, this 1-bit signal, needs to be translated into the high voltage 2.5 for the thick oxide transistors. To do this, we use a level shifter. So these levels plus minus 0.1 volt will be translated to 2.5 volts and then half range. And then this is fed to a CML driver, which will adjust the levels of the signal to be good for the current switches in the DA cell. So all these transistors are thick oxide and these are thin oxide. Then this is the floor plan of the whole DAC cell. Here it is the digital part. Up to here we have the thin oxide digital transistors, at 1 volt, and we have a very good isolation between the analog part and the digital part. So here the switching is very active, CMOS switching, generating a lot of disturbance, while here in the analog part we keep everything quiet and clean. For digital gates we use CML logic, for which only constant current is consumed, and we don't have switching of current in the power supply. The synchronization, the timing synchronization, is done in digital domain, thin oxide transistors, low voltage, so that it is very accurate. We have smaller, lower parasitics in thin oxide transistors, and we can have very accurate timing. Now, yeah, I already said noisy CMOS logic is isolated. Look at the whole DAC area, it's just 0.037 square millimeters, and here the areas of each block are given. Another particular thing that you should pay attention is the area of the array of current sources. It's only 0.0076 square millimeters, and this is because we use calibration. So the current sources are designed with smaller area, and of course if they are small in area, their mismatches will be large, but we can calibrate their mismatches. That's the trick. So you see that the calibration, okay, we add a little bit of calibrating like this block, but still this allows us to design a very small area array of current sources. And you can see here the areas of the current sources actually are given. If you compare this with other papers, you'll see that here we gain a lot of area by allowing small arrays of current sources. Then we put this 12-bit single DAC cell together with 16 others. Yeah, so these are 16 cells. And then you see that it's very compact, rectangular shape, so that integration is enabled. But in the measurements, of course, this is a test chip. In the measurements we couldn't really measure the full potential of such an array, because we are limited with the initial problems of how to get digital data for 16 D2A converters, and how to get in a more flexible way their output and combine it together depending on the application, of course. So for our measurements, what we did is that we measured a single DAC cell performance, and also as an illustration a combination between two DAC cells used together as a single 13-bit DAC. What does this mean is illustrated here with this INL. So you see here the pattern of a single DAC cell, and we stack on top of it the other. You see that they are different D2A converters, even though they are adjacent to each other, and their gain errors are different, and their pattern here in the binary current errors are different. However, if we run the calibration, they are aligned. So yeah, in real life it will not be used like this, but this is just to illustrate the big mismatches that exist between DAC cells and how the calibration can help. Then this is a measurement of SFDR, spurious free dynamic range. 1 gigasample per second, so the Nyquist band is from 0 to 500 megahertz. And what we have here is just the performance of a single 12-bit cell, and this combination of two stacked D2A converters to create a virtual 13-bit DAC. So what you see here is before calibration and after calibration. So before calibration, you see that the 13-bit mode is even worse than 12-bit, and this is because of the large gain errors. However, when we calibrate both, the performance is improved by about 8 dB. This performance is kept up to 50 megahertz, and beyond that dynamic errors start to kick in, so the performance decreases, and it again stabilizes to a level of around 50 dB, 55 dB at high frequencies. So this is the sweep of AMD3. Again, what we see here at low frequency, the performance without the performance before calibration is about 10 dB lower than the performance after calibration. When we calibrate, the AMD3 improves, and then these disadvantages are kept to about 100 megahertz. After that, as the timing errors and the dynamic errors become dominant, the advantages of the static calibration are lost. So here are some spectra to see. This is at center frequency of 80 megahertz, and spacing between the two tones of 1 megahertz. So here we will measure AMD3, and then before calibration we have 72, about 72 for this particular point, and when we run calibration there is a 10 dB difference improvement. See how clean the spectrum is after calibration. So this is at 80 gigahertz, and if we push this to 350, which is kind of big performance for this D2A converter, we can measure AMD3 of about 60 dB, around 350 megahertz. Then to compare with literature, I have this table. So our goals for this design, to enable, for example, massive arrays for 5G, for digital beamforming, we need small area because we want massive arrays integrated in a single chip. We want wide bandwidth and high linearity because these are for telecom, for wireless communication. Then this is, of course, as shown, enabled by the calibration, and the calibration actually allows us first to use large binary segmentation part, which makes the whole architecture of the D2A converter very efficient in both resources, area, and power consumption. And so this is one. And the second thing is that the calibration allows us to design very small transistors, arrays of current sources, which will feature unavoidably large intrinsic matching errors, and the calibration will improve these. And this leads us to this very small area. If we look with the others, what the others are doing, we'll immediately spot this D2A converter, so published 2019. However, if we look closely, you see the performance here. And the reason is that this is oversampled DAC. So this is digital sigma delta, and which uses high oversampling ratio, and this results into a very small bandwidth. If you look at some recent publications in a very advanced technology such as 16 nanometers with amazing performance, still the area that is needed is about 10 times bigger than ours. And this is even though the difference in the technologies, 16 nanometer versus 40 nanometer, but effectively implemented at 250 TOPS. And the major difference, of course, is the choices about the architecture. So our binary architectures, and the calibration, of course. So in conclusions, Let me briefly repeat that binary DAC architectures are efficient in terms of both power and area. Then calibration of errors, however, is necessary to compensate for their deficiencies, and calibration enables binary architectures with our algorithm for binary current calibration, and it also allows small current source arrays, which reduce the size of the DAC cell enormously. Then massive integration will become possible. But further validation is needed. We integrated 16 D2A converters, but we couldn't really measure these so far in a phased array setup. This is work for the future. And here are the references that were used in my presentation. Thank you very much for your attention. Bye.